today we are in the last plenary talk of the conference. So today we have Dr. Krishnendu Gangopadhyay from IISc Mohali, and he will be the chair for this session. Yeah, over to you, Krishnendu.
Okay, so good afternoon, everyone. It's a great pleasure. So today is the last working day of this virtual math fest. Tomorrow there will be a panel discussion and valedictory function, but there will be no more academic, formal academic talks, I say. So I thank Professor Siddhartha Gadgil, who is our plenary speaker today, for accepting our invitation and for giving this talk. So Professor Gadgil works in the broad area of low dimensional topology. So he did his PhD from California Institute of Technology in 1999. And after that, he held positions as a postdoc in Stony Brook and then joined Indian Statistical Institute as an associate professor. So currently he is a professor at the Indian Institute of Science, Bangalore from 2012. So Professor Gadgil has a broad, versatile interest. So he is one of the very versatile mathematicians of the country. So these days, I mean, he is also working in areas which we like to call interdisciplinary areas. Like you can see from his title, it's a combination of geometric topology and some aspects of biology. So I welcome Professor Gadgil to deliver his talk. Thank you.
Oh, thank you very much, Krishnendu, and I should thank the organizers for, of course, inviting me to speak, but also for organizing these things. I mean, very unfortunate circumstances have resulted in organizing these, but I think this is a wonderful thing even in happier times, especially it saves travel, it saves jet fuel and the costs of air travel, but also in India, especially, you can reach far more people this way. It's wonderful. Hopefully these things will continue even in happier times, maybe along with the more personal events. Okay. So this talk I'll be turning off my video soon because my network is not great. And if I keep my video on, you may not hear me so well. Okay. So let me begin. So this talk is going to be about various things, about free groups, mostly about free groups. It has some little relation to RNA, which I will begin with, but it's not really biology in this case. I mean, the biology is very real, but the results aren't really biology. Okay, so this is joint work with Manjunath Krishnapur, my colleague at IISc Bangalore, who's a probabilist. And this follows up on work that actually I did a decade ago, and then it was dormant for a while. And then Manjunath and I did this work, and then it was dormant for a while, and then we again got improved results recently. The improvement was actually prompted by Polymath 14, which some of you would have heard of, which was a very enjoyable collaboration on the internet, which involved many of the same things you will see today. But I won't say anything more about that particular thing. So that kind of revived this, and then here's what we're talking about. Okay. So let me begin the story with RNA and ribonucleic acid and secondary structures of RNA, to be specific. So what do I mean by secondary structures of RNA? So these macromolecules, DNA, RNA, proteins that you have, they're all long strands, and they are strands made of specific smaller units. In the case of proteins, these are amino acids. There are 20 of them. Now there are some more synthetic ones as well, but in nature there are 20 amino acids. These 20 amino acids form a strand, and that strand then folds up. It folds up first by forming bonds among itself, forming what's called a secondary structure, and then eventually a tertiary structure, which is a three-dimensional geometric structure. And one of the fundamental problems in science is understanding how the linear sequence of amino acids results in a three-dimensional geometric structure. So input and output are purely mathematical in this case, but we really have very little idea of how this does. Now DNA, as you all would know, has boring secondary structure, meaning it's not boring, it's a double helix, which is wonderful as an information store. It allows replication and it allows stability of information. But that's about all. On the other hand, the proteins folding into complicated structures allows them to perform the role of enzymes as catalysis. Okay, but here I'm going to talk about neither DNA nor proteins, but RNA. Now, in the original central dogma, as it was called, in the original view of molecular biology from the 50s and 60s, the main role of RNA was just an intermediary. That is, it translated, carried, etc. messages from DNA to protein. So DNA told you the information, which was like an abstract code, and proteins translated that into a structure, they folded, and they did the real work. Okay, and RNA had that value in between. But then one knows two other rules that RNA has. Okay, so one of which is that there are viruses where RNA is the store of information. There is no DNA at all, including what is currently the most unpopular organism, at least in to our species, the SARS-CoV-2, the virus that causes COVID-19 is an RNA virus. So it has no DNA. It uses RNA as its store of information. But also even later it was discovered, that this is not new now, this is 20, 30, maybe even 40 years old, though in more recent times the roles have grown, that RNA can also play the role of catalysis like proteins. So like you have enzymes, you have ribozymes. And in particular, the ribosome is believed, earlier they thought RNA was just structural and proteins do the work. It's now believed that the ribosome, which is where proteins are synthesized, it's the other way around. Proteins are just helpers. The real work comes completely from RNA. Okay, so these were biological preliminaries. I'll just say one last thing about this, which is that today, of course, ribozymes are important, but there is another role. If you go back to the origin of life, in the origin of life, this used to be a mystery that you have a chicken and egg situation. DNA as an information store, is like the theory is useless without the proteins doing the real world work. And proteins are useless without the guidance as to what they are supposed to do in terms of what shape they have. And so how would one evolve without the other? But now that we know RNA is can do both the roles of DNA and proteins, it is widely believed that RNA was once playing both these roles, that you have, it was both the catalyst and the store of information, and the world was an RNA world. Perhaps it was a somewhat similar molecule rather than RNA, which started and then RNA world took over from that. But nevertheless, so both in today's world and in the origin of life, RNA is quite very important. Okay, and in particular, the catalysis of RNA, just like catalysis of proteins, depends on secondary structure. So understanding RNA's secondary structure is a fundamental problem in biology. Okay, so what we'll be looking at, I'll be precise in a moment, is a simplified model, but not a silly model. It's close enough to the reality of RNA. We won't answer any biological questions though. Okay, so we'll just do mathematics inspired by the biological question, but inspired in a real sense. So let's look at this RNA. So there are two pictures here. This one, the yeast tRNA here that you see, is just an elaborate picture. But what we'll look at in more detail is the helical junction, which is a little piece of it. Let's see how it looks. Okay, so let's take the single strand. And now I'll straighten this out. And we'll think like topologists. That is to say, we don't care about the geometric shape, we care about the topological shape of these. So let's look at these guys. So if you see in the strand, the top strand of this is here and the bottom strand is at the end, final end of this. And this bond here, for example, becomes an arch, which starts here and ends here. Okay, let me try a slightly better arch. It starts here and it ends here. Inside it is another arch. And a lot of them, okay? But let's turn to another thing, which is, let's look at this region, which is now purple. How does this guy look? Well, it comes soon after this. It will give you arches like this, soon after this guy. And let me take orange or something like that. For this helix, oh, I haven't switched colors. Here it is. For this helix, so that's why the term helical junction. You end up with pictures like this. Okay, So you see some nice geometry here. Okay, I've straightened this out and I'm simply noting the bonds. The key point to notice is that they don't cross each other. Okay, that is the one point to notice. The other point to notice, which is basic biology, is almost all the bonds, if I see an adenine here, okay, so suppose this was adenine, then on the other end, I'm bound to have uracil. Okay, uracil plays the role of thiamine in RNA. So ATGC is something we would all have studied in our school biology, and you know this is general knowledge. So you have an AU, in this particular case, the next one is a UA, that it could be a GC. Okay, so most of the bonds connect A to G. Oh, sorry, not A to G, of course, A to U and G to C. Okay, so these are the Watson-Crick pairs. Like in the case of our DNA, this would be T, thiamine, instead of uracil. So you have two features here. One of which is that you have this nice non-crossing matching. So you have these bonds, they're non-crossing. And the other feature that you have is that the pairings are of a very specific sort. Adenine pairs with uracil and guanine pairs with cytosine. Okay, and we want to understand the secondary structure. Now, this will not tell you very well because of the approximation, the secondary structure of a specific molecule. It might still tell you something about it. I haven't checked with experimental data, but it's certainly at a conceptual level, if you're thinking of the origin of life or many other functions that the RNA does, a good model may tell you something. Okay, I'm not going to speculate on what it will tell you today. I don't know. But we'll soon move completely to a mathematical model. But first, let me just say what I said earlier. The Watson-Crick pairs, AUGC, are the strongest bonds that you have for an RNA molecule. And stereochemical forces oppose what are called pseudoknots. Okay. So, it's very high. So for example, if I have this guy is blue, and let me again take a straight line. Here, in this case, the blue guy forms some bonds, 3 of them, but let me just draw 2. And let's look at the orange guy here. It forms some bonds. And now you trace, you see you get a blue stretch and then soon you get an orange stretch. So in fact, these cross each other. Okay, this is what is called a pseudo-knot. Of course, if you're a topologist, it looks more like genus. And indeed, that's what it is. If you think of these as fat graphs or something like that. So these are pseudo-knots. So, but while there are pseudo-knots in nature, just as there are wobble pairs, that is pairs which are not AU and GC, but I don't know which are the wobble pairs. I think G and U pair together to form a wobble pairs. So just as there are other pairs, there are also pseudo-knots, but both of these are rare. That is to say, to a reasonable approximation, you can think of RNA as folding in such a way that you bond as much as you can without allowing pseudo-knots, okay, which is topologically very nice, it's crossings, and where the pairs are all Watson-Crick pairs. So henceforth, we'll take that as our model. Okay, so right now we'll move away from biology. To summarize the biology we have seen so far is simply that RNA is very important. In particular, its secondary structure is very important to understand because of its role in catalysis and so on. And what we have here is a very reasonable model of the secondary structure. Okay, but something which becomes mathematically very nice. So this is what I find attractive about RNA, though I'm not currently working on this very much, which is that something which is biologically reasonable translates to something which is mathematically not complicated. And why I'm saying nice, you'll see soon. I think already this is relatively nice, just 4 letters and a condition that we will like, non-crossing, whether you're thinking combinatorially or topologically. Okay, so here's the picture. Just for fun, this is computer generated. You'll see letters A, U, G, A, etc., etc. So here's the randomly generated RNA. This is not actual RNA, but the same alphabet. And you see matching. The colors will tell you what the bond is, what the left and right hand side are. They have no particular biological significance in the sense that AU and UA have different colors. for just visual effect. You'll see 4 different colors depending on both on what is left and what is right. This is just, so this is our model we have. We have a string and we have things that go from left to right, meaning arcs like this, and they don't cross. So this is a nice picture. This is the picture we want to understand. Okay, so now with this we'll move to a slightly, with this we leave biology. We'll come back to it if there are any questions at the end. Completely, we have a completely geometric topological combinatorial problem where we have a linear string of letters and we are looking at non-crossing matchings with this constraint. Okay, and what is nice is we can make this algebraic. And so if I identify A with alpha and U with its inverse alpha bar, and B with beta and G with beta and C with beta inverse. Okay, so now these guys alpha inverse and beta inverse are simply formal inverses. Okay, they're not actually inverses in anything, but as you know, you can put these formal inverses in the free group. So what we'll be looking at are, these are letters. You can think of them as alpha, beta, alpha inverse and beta inverse. And we are looking at words in these letters. So as far as words are concerned, they're just letters. But when we look at them as elements in the free group, which we will soon, you think of alpha cancelling with alpha inverse and beta cancelling with beta inverse. And let me remind you, in the free group, there is no other relation. So now then things are very nice. It's not just that letters are matched with other letters, but specifically letters are only matched with their inverses and there are no crossing. Okay, so let's take the energy. This is a biologically reasonable notion of energy, is the number of unmatched letters. So you want to match as much as possible. You want to minimize potential energy. The potential energy is given by unmatched letters. So given a word, we'll look at the minimum number of unmatched letters. There are also lots of non-crossing matchings. It is a very rich structure, and we'll look at the minimum number of non-crossing matchings. Okay. So what properties does this have? So now let's do some work. First point is, this depends only on the equivalence class W in alpha beta. Okay, so let me quickly sketch a proof of this. So what we are trying to say is that if I look at a word, so remember the equivalence here is, if I look at G1 and alpha bar G2, this is going to be equivalent to G1 G2. And this is the basic equivalence. Up to symmetry, I can as well assume that. Okay, so what I want to show is that the length of, let's draw it like this. So this part is G1, and then I have alpha bar, and then this part is G2. Okay, I want to show that this is equal to length of G1, G2. Okay, let me dispose of the easy part first. Okay, so the easy part I'll just use this like a board, is that the length of the, when you add this pair, you do not increase the length. So this is actually the easier part, even though the left hand side is a longer word. That is because if I have a non-crossing matching of G1, G2, okay, so let's just take some arcs. Maybe some of the arcs are like this. Some of the arcs may go from G1 to G2. Okay, I may have some arcs like this and some arcs like this. You notice that I can just make the same corresponding arcs. Ignore alpha and alpha bar. If I had an arc that went from this to this guy, I'll have a same corresponding arc here, and then this one, and then this one, this one, this one. And in addition, let me color it in purple, have a new arc which is alpha to alpha bar. So what I did is I simply took the same arcs. By same, of course, I don't mean literally the same indices. I just shifted if you have alpha bar in between, and then added, I don't know if my 2 pictures are correct. Yeah, but I just added alpha paired with alpha bar. Now, how many guys are unmatched here? It is exactly those that were unmatched earlier. So if these guys are unmatched here, they continue to be unmatched here. Alpha bar are matched. So what this tells you is, suppose I take a non-cross. So remember, the length is the minimum number of non-crossing matching. So I can take a non-crossing matching with the number unmatched being the length. Okay. Yeah.
Siddharth.
Yeah.
Sorry for the interruption.
No problem.
So there are many questions actually. So
Okay,
all of them have a common question.
yes.
What is matching? Could you please define what
Oh,
a matching is?
thank you. Thanks for asking the question. Let me go to this picture. Matching is something like this, okay? So matching means that I have a word, okay? Thanks. So I have a word X, okay? So this has letters, let's say X1, X2, Xn, okay? So matching will mean M is contained, so it's contained in pairs. Okay, so matching, so let me call this N as 1, 2, N. Okay, so M is contained in N cross N, literally. Well, okay, more than that. So M is a subset set of pairs Ij, and 1 is less than or equal to I is less than J is less than or equal to N. This is the formal way of saying matching means I decide that C here is matched to this G here. This G here is matched to the C that sits next to it, etc., etc. Okay, so if I have a linear sequence here, just of indices of letters, a matching means that I just choose pairs, and those pairs are matched to tell me that one letter is matched to the other, with the condition that the pair should be disjoint. So a letter can't be matched to two different things. The other condition is that a letter can only be matched to its inverse, or in this picture, it will be guanine matched to cytosine and adenine to uracil. So matching would mean that Xi and Xj are complementary, that pairs are distinct from each other. Okay, and for definiteness, we can say the first element is before the second element. So things are not matched to themselves, they're matched to other things. So matching is a collection of pairs which tell you what is bonded to what. So the picture is what arches, left end of the arch is mapped to right end of the arch. Or if I took a bond in the previous picture, it's here, it is that this adenine is matched to you. So it's where the bond is or where the arch begins is mapped to the arch. Okay, is this clear or some other questions? Yeah.
Is there any other doubt? Then you can ask to the speaker. Okay, that's what people are saying is clear. Thanks.
Yeah. Okay, thanks for asking the question. I just forgot that I had not said clearly what matching is. So matching is RNA bonds. In this case, it's arches. Okay, so saying that, let me get back here again. So identifying these with the letters alpha, beta, alpha bar, and beta bar. Okay, then RNA secondary structures, they correspond to matchings, which means letters matched with other letters. Okay, such that letters can only be matched with their inverses and there are no crossings. No crossing you can formally define in terms of inequalities, but you see the topological picture also. Okay, and as I said, what we try to do is what RNA tries to do when it folds, and what we are going to look at mathematically as a length is look at all non-crossing matchings with the condition that letters are matched to their inverse. For each one of them, there's a certain number of unmatched letters. And I'll take the minimum of these. The minimum is not unique. There'll be many non-crossing matchings with that. But the number of these letters, what is the minimum number that are unmatched? Okay. So if you want, while we are here, let me just put an example in this guy. So for example, if I had a word alpha, beta, and then I had alpha bar and beta bar. What is the best matching I can find here? Well, I can match alpha with alpha bar, for example. But now beta and beta bar are left unmatched. Okay, that's because if I try to match them, I'll be forced to have a crossing. Otherwise, I could match beta and beta bar, and then alpha and alpha bar will be matched. So the length of this, as I'm calling L in the next slide, is 2. Because the minimum number of non-crossing matchings is, minimum number of unmatched letters is 2. Of course, if there are more alphas than alpha bars, for an elementary reason, some alphas have to be unmatched. But this is an interesting example because it's the non-crossing condition that forces things to be unmatched. And this is what you immediately realize is a little bit of a subtle notion, this number of non-crossing matchings. It's the non-crossing condition is a subtle topological condition, if you wish, but it's a subtle condition. Okay. So again, now to come back to this, okay, what do I want to show? What I want to show is in the free group, okay, the condition is, let me redraw this and make it, let me make this in 2 lines. Okay, I was trying to show this in just 1 line. Okay, so this is a short lecture, so please feel free to interrupt. So what I want to show here is that, so if G1 alpha bar G2 is equivalent to G1 G2. This is true in the free group, and this is the only relation in the free group. So given this relation, what I want to show is that the length of G1 alpha bar G2 is equal to the length of G1 G2. And of course, a common way of showing such inequalities is to show 2 equalities. And let's show 2 equalities. Okay, so let's take first of all length of, let me take a line here. Okay, let me be lazy and draw the other line here also. Okay, so what did I have on the left hand side? Okay, so let me, that line is longer. Okay, so that's all right. So if I have G1 here, and then I have these 2 points, alpha 1 and alpha 2. And then here I just have G1, G2.
Yeah, so there is one more question.
Yeah.
So could you please, could we have a formal algebraic definition of a crossing?
Formal algebraic definition of a crossing. Okay.
Yeah.
So let's do it here as an exercise. Let me find, I know where I'll find. So I've kept blank paper at the end for these questions. Okay, let's just work it out. Here we are. Okay, here's the line. Okay, so I have I here, I have J here, I have K here, and I have L here. Okay, so crossing means we have pairs IK and JL in the set of all matchings. Okay, so IK and JL, and they cross such that I is less than J is less than K is less than L. So here's a formal algebraic definition of crossing, if you wish. So crossing is a set of pairs. So M, if we want to be formal, let me write what M is a subset of. M is a subset of all pairs. Let me not use I and J, which I've used, AB, such that 1 is less than or A is less than B is less than N. Okay. So M is a subset of these. So these are matchings. We have the additional condition. So we require XA is XB bar. Okay, so we require the letters to be inverses of each other, but that has nothing to do with crossing. So crossing is a geometric condition. This is the condition letters paired with their inverses. Okay, so here's a formal definition of crossing. You simply write this as this inequality. Yeah, is that clear, or any other questions?
No, I think it is clear.
Okay, yeah, so thanks for all the questions. Yeah, I've kept the material. Okay, so back here, let's try to see. We want to show that L of this, which inequality were we in the middle of showing? So the easier inequality is actually that the longer word is shorter. Okay, so somewhat, so that it is, yeah, that's right. So remember, L means that there is a non-crossing matching with exactly these many unmatched. Okay, so let's draw such a non-crossing matching. It might look something like this. Now I've drawn a slightly simpler picture than I did last time in some sense. Okay, so you simply find the corresponding non-crossing matching here. This one will jump over alpha beta. Oh, the picture looked more like this. Like this. So you see, you can translate the picture on the right, non-crossing matching, to that on the left, simply by shifting indices. So whenever you have an index which is either I or I plus 1, whatever, the index of alpha, oh, I've written alpha 1 and alpha 2 here because of course, they have to be inverses, which without loss of generality are alpha and alpha bar. There are 4 cases. And then we add one more matching, one more pair. So our matching consists of the old ones shifted and the new ones. And now obviously something is unmatched here, means it's already unmatched in the same place here. Okay, alpha, the new letters are matched. What this tells you is that the number of non-crossing matchings on the left, unmatched letters on the left-hand side is less than or equal to the number of unmatched letters on the right-hand side, which was chosen to be the length. And so maybe there's a way you can do better than this. Okay, so all you know is the length, which is the minimum, is less than or equal to these. Okay, so now let's try the other way around. So again, yeah, so I was a little quick through this, but okay, so let's take the length of, okay, this time I'll make sure that I have space is greater than or equal to length of this. This is more complicated. Let's get some lines here. Okay, and as you remember, let's break it. And here we break it like this. Okay, let me break them closer to each other. Okay, so what this means is this guy is G1, this guy is G2, this is G1, and this is G2. And here we have alpha and alpha bar. Okay, and what I want to show is that this length is greater than or equal to these. And this actually has a subtlety, because if you look at a non-crossing matching of the left-hand side. So on the left-hand side, we have a non-crossing matching. So number of unmatched letters is the length. That non-crossing matching may have some things like this, and then maybe something like this, and maybe something like this. But crucially, alpha and alpha bar may be matched to some other letters. Okay, there are different geometric configurations, but I'm just sketching an argument. It's easy to formalize this. So alpha and alpha bar may be matched to these letters. So if I delete them, what happens is that these two matchings go away. And so this guy and this guy, if I just simply delete alpha and alpha bar, I'm be forced to delete things. So two additional guys end up being unmatched. And this is not good. So now then what has happened is those that are unmatched on the left-hand side remain unmatched, and then two additional guys remain unmatched. Alpha, alpha bar have gone away, so their matching doesn't matter. Well, the trick here is that you can rewire. So if I see these two arches, then what I can do is I can go from here like this and like this. And if you wish, I can think of alpha and alpha bar as being paired to each other. So given a non-crossing matching on the left-hand side, I can change it so alpha, alpha bar are paired with each other without increasing the non-crossing matchings. Okay, there's a couple of other cases, but those cases are easier, where one of alpha and alpha bar is not matched at all. Then you can simply delete. But if both alpha and alpha bar are matched, you have to do this slightly elaborate, you have to do this rewiring. And this rewiring, excuse me, will tell you so that you have a matching. So alpha and alpha bar are matched, and the number of unmatched letters is the same as the length. Once I have this, I can just delete the red arc, and sorry, so the orange, now these two letters are paired with each other. They went from being red to orange, and there is an orange arc connecting them. Simply delete alpha, alpha bar and the red arc, and now the number of unmatched letters on the left hand side is the same as the number of unmatched letters on the right hand side. So that shows this inequality. Okay, so this was a crucial part of showing that this is well defined. Okay, so what we showed here is that this is well defined. Namely, that if two words give you the same element in the free group, that is, they're related by cancellation. By the way, alpha bar is alpha inverse, let me remind you. So if they're related by cancellation, the length does not change. So this length is actually a function on the free group. What I have not told you is what I mean by saying it's a length and proving that it is a length. That we'll come to next, because that will be also an ingredient of that will also be a crucial in the proof of the main result. Okay. Also, conjugacy invariance. By the way, conjugacy invariance, the picture is very similar to the picture that we have for. Sorry, I'm searching for my pen. So what does conjugacy invariance mean? It means I have a letter G here, and then I have alpha here, and then I have alpha bar here. So this is actually just like alpha and alpha bar next to each other, except cyclically. So exactly the same proof will work. So you can take it as an exercise. If you understand this proof, that is to say, you can find a matching where alpha and alpha bar are paired with each other by rewiring. So it's the same proof, except that here they're next to each other, they're at the other ends to each other. What I have not established is that it's a length, and I haven't even told you what I mean by length. Okay, so a length function on a group must satisfy the following. This is more or less like a norm, except for abelian groups. The length of the E, the identity is 0. Okay, here that is very easy, because E is the empty word. Take the empty matching, nothing is unpaired. Length of G inverse equals length of G. That is again easy. Just make a mirror of it. Okay. The third one is not hard. So let's look at this. Namely, if I have G and H, and if I have a non-crossing matching for G, it may look like this, and I have a non-crossing matching for H, just put them next to each other. You get a non-crossing matching for GH. The unmatched letters are those that are unmatched in G and those that are unmatched in H. And so the number is going to be the sum. So you take one's optimal one on the left, optimal one on the right, just next to each other. The final thing is often trivial, but in this case, this is also a lemma in the proof of the main result. I haven't told you stated the main result yet. So I'll spend a couple of minutes saying what this is. That if the length is 0, then G is E. Okay. So recall what the length means. The length being 0 means. Length being 0 means that there is a non-crossing matching with nothing unmatched. Every letter is matched. Okay, so here let me draw a little bit of a non-crossing matching just for the sake of doodling. But all the letters are matched here. Okay, so there is nothing other than the end points of these arcs. Well, what we'll do is we'll look at something like this, which is an innermost arc. Now, because it's a non-crossing matching, there cannot be a letter in between here, because if there is a letter here, it'll have to cross to match somewhere else. Okay, if there are two letters here matched with each other, then this arc is not innermost. So you can look at the innermost arc. Formally, you just look at an arc so that the difference between right endpoint and left endpoint is minimum. This is a finite set of differences. You look at one which is minimum and claim that the left endpoint and right endpoint for such an arc should be next to each other. But also remember they're inverses of each other. So they must be of the form alpha, alpha bar, or maybe for a change, maybe they were beta bar and beta. Okay, so look at an innermost arc, and then you have beta bar and beta. So they can cancel, and you induct on the length. And from this, you can show that you have a series of cancellations. Your non-crossing matching will give you a series of cancellations, which will take you to the trivial word. Okay, so if the length is 0, that is, if there's a non-crossing matching with nothing that is unmatched, then it has to be a trivial element in the free group. Okay, this will come later. That's why I spend some time proving it right now. Okay, this will be one of our key lemmas. Lemmas for what? Okay, so this slide is a digression. Yeah, question?
Okay, so
yeah.
Sorry, there is one more question.
Yeah.
So why are we particularly transfer the model of RNA in two-dimensional setup? Why not in three-dimensional to avoid such crossing setup?
I did not actually assume it's two-dimensional. All my pictures are two-dimensional, but if you write it as a formula, it's a set of indices. Okay, and the condition of non-crossing is so the condition of no pseudoknots becomes, if you wish, a two-dimensional non-crossing condition. Okay, so pseudoknots translated to two-dimensional non-crossing And that is nature, that is biology. It's correct biology that there is stereochemical resistance to pseudoknots. As I said, it's an approximation. There are a few pseudoknots in an RNA molecule. Many of them have none at all. Some RNA molecules have some pseudoknots, but it's a rather good approximation to say no pseudoknots. That just translates to this. It is not that I chose a translation. I chose the approximation, but it is the strongest positive force and the strongest negative force was my approximation. It just mapped to this. Yeah.
Okay. Okay. I think that answers the question.
Yeah. Yeah. Okay. So to go on, we know this is a length function. In particular, if the length is trivial, it's a trivial word in the free group. And my next slide is a bit of a digression. This is what I did many years ago. So what I call Watson-Crick length is, so it has some very attractive properties here. So I defined it explicitly with non-crossing matching, but here are two algebraic definitions of it. So you can go from, we started with RNA, we went to combinatorics and geometry. Now we are going to actual algebra. Let's look at lengths which are conjugacy invariant. So length of GH, G inverse is the same as length of H. Okay. And so that the generators have length less than or equal to 1 or equal to 1, both will give you the same result. Look at all such lengths and look at the largest such length. This is a very Gromov style of defining things, that you look at the largest length. This turns out to be exactly the Watson-Crick length. I'm not going to prove this today. We can discuss later if you want. It's in these papers. And it's the maximum among such length. It also has another purely algebraic definition. So the generators, of course, alpha, beta, and their inverses generate the free group. But I can look at a bigger generating set, which is not just alpha, beta, but it's conjugates as well. Okay. And then I look at the word length, which is how many generators do I need to write a given word. This is less than that in the original generating set because we have more generators, but it is a length. And this L Watson-Crick length is also exactly the word length in this generating set. Okay, 1 and 2 being equal, you can see, but the nice thing is these two purely algebraic definitions, which by the way are also related to what's called the edit distance, the equality between these two. I should thank Apurva Khare, because of him I know some the relation between 1 and 2. It's well known. It's not that he discovered it, but it's thanks. I don't know if he's in this talk, but if he is, yeah. I know these two are equivalent because of this. But so you have two algebraic characterizations of the previous length as well. Okay, so what we are studying is a mathematically very natural object. It has some nice geometry. Okay, so now we want to find lower bounds on length. That is the key thing. And there is an obvious lower bound, which is your abelianize. Namely, if there are more alphas than betas, or than alpha bars, or more betas than beta bars, or the other way around, okay, then you will end up with some alphas not paired, because alphas have to match to alpha bar. This is kind of obvious thing. And what I worked on long ago, and I'm not going to say anything more about it today except to state this, is that to me, this looks just like linking numbers in topology. Okay, it does. It is formally the linking numbers. And Milner, in his both undergraduate thesis here, constructed things called Milner invariants, and he has further things in his PhD thesis, where you look at not abelianization, but extend linking to higher linking. Okay, which is you look at quotients in the lower central series. So in particular, if you look at the first term in the lower central series, you get a number associated to this. This is also geometrically nice. It's an area, what I call Heisenberg invariant. Okay, so that F over F3 is a nice group in particular. And this is a story I won't go into today any more than this, to say that I did this long ago. It is interesting. There are interesting things you can do with the length, simply from an algebraic viewpoint of view. Okay, and there are people who work on conjugacy invariant lengths, including Arpan, whom I know is there. And they're very non-trivial things, relations to stable commutator length and quasimorphisms and so on. So here we are looking at something which is nice mathematically and even studied mathematically. Okay, so let's go to the question of the day. Okay, in 15-20 minutes, I will try to explain. Here's the question of the day. This is joint work with Manjunath. I started discussing with him soon after he joined our department, actually, and then it lay dormant for a little while. So here we are. Let's take a random word in alpha, bar, beta, bar, by which I mean alpha, bar, beta, bar, each have probability 1/4 of being a given letter, and they're all independent of each other. How does L behave for a random word? Well, not a specific random word. How about the average? So let's look at all random words of a given length. Look at the average. Of course, these words are getting longer. So we want to look at average normalized by n. This means this is the proportion of unmatched letters. If I take a long word in the free group, or RNA if you wish, and you take the best matching, what is the behavior of the proportion of words? Well, there is something called Fekette's lemma, which tells you that because L bar n is what is called subadditive. Okay, so let me just write down that formula. I don't actually need this. So what we know is L bar n, n1 plus n2 is less than or equal to L bar of n1 plus L bar of n2. And the reason for this is if I took a random word here, I could take a random word here xn1, and I could take a random word here xn2, and I put them together, I get a random word of length n1 plus n2. Okay, and triangle inequality, or more directly looking at non-crossing matchings followed by non-crossing matchings here, will tell you L bar of this random word is less than or equal to L bar of those two. Okay, so this is subadditive, and if it's subadditive, we know this limit always exists. So that's very well. The crucial question is, what is the limit? Specifically, is it a positive number or is it 0? And in probability, it being a positive number has strong consequences. That is, asymptotically, is the number of unmatched letters or fraction of unmatched letters, is it asymptotically a positive number or is it 0? Okay, so this is the question that we are going to address today. Okay, so here's our theorem also. Yes, so namely that if I look at rho of n, which is this average, it converges to lambda 2. The 2 is because this is the free group on 2 generators. The same result, as I'll say in the end, works for any free group, finitely many generators at any rate. So, sorry. So if I look at rho of n, it's this average, it goes to a positive constant. Okay, so first of all, the average number, to show that the average number is positive, it's bounded above by, you can see, n lambda 2 times probability of where is my highlighter? It's bounded by this. This is elementary, and so you have, so it's enough. So let's take n to the other side. So expectation of this by n is greater than lambda 2 times this probability. Okay, and so it's enough to show this probability goes to 1, or equivalently the probability that, now the final statement you can concentrate on if this is not obvious to you. The final statement says that if I take a word of length n and think of lambda 2 as 1 in 100, it says what you have to show is just the probability that at most 100th of the letters are unmatched. Very few are unmatched. Just 1% of the letters of unmatched goes to 0. If for any lambda 2 you can find this, you know expectation is greater than or equal to lambda 2. Okay, so this is the first reduction. So we have to bound the probability that a given random word has in its optimal matching a very tiny fraction that is unmatched, where that tiny fraction is the fixed number as n goes to infinity. We'll prove this by counting words, okay, that have non-crossing matchings with only a small fraction unmatched. Okay, let's get to counting. So first observation, if you have the right parity condition, so m is the number of matchings, okay, then r, which will be the number unmatched, n minus 2m. So if you have a non-crossing matching with at most r unmatched letters, if there are at most 100 unmatched letters, maybe there were 96, then you can find another with exactly 100 unmatched letters, throw away a few matchings. Okay, simply by dropping a few. This of course doesn't change the parity. That's why I stated that carefully. That is, if you had 97 unmatched letters, then you would get 101 unmatched letters. So your parity cannot be affected, but parity is just determined by n. So as long as, because the number of matched letters is always even, but as long as your parity is correct, if you have a very good matching, just throw away a few pairs and you got this. So what it suffices to show that if m is this appropriate quantity, that is the number is almost everything is matched for some appropriate m, and r is the n minus 2m, then the fraction of words with non-crossing with r letters unmatched is small. Okay, so again, you have 1,000,000 letters and your n is say 1,000,000, R is 1,000 because my lambda 2 was 1 over 1,000, let's say. Then what you want to show is that the number, the fraction of words with matching with only 1,000 unmatched is small. There are not too many such words. Okay, so we'll find an upper bound on this. So the n of nr, which is number of words with r unmatched letters. And just remember the total number of words is 4 to the n. So n of nr should be small compared to this. Okay, so let's see what this is. So here is an idea. Okay, so we tried various things, and this is one way of, actually there are other equivalent combinatorial arguments, but this is one way that works quite nicely. Oh, sorry, I don't have a highlighter. So let's look at our word X. Okay, so this is X. Now some letters are matched, and some things are unmatched. Okay, and there'll be segments that are unmatched. So what I'll do is the matched letters, this guy, this guy, this guy, this guy, take them in the order they are here. Okay, and they constitute Z. These guys continue. So this guy is Z1, Z2, Z3, etc. And I haven't marked them here, so let me mark them. There are certain letters that remain unmatched. Maybe there's one here, maybe there's one here, maybe there's nothing there, maybe here. Okay, so the purple guys constitute Y. So this guy is Y1, Y2, etc. So this is some Y. We know the lengths, by the way. So the number of unmatched letters is R. So Z has length 2m, Y has length R. Okay, so I'll just look at the letters that are matched and the letters that are unmatched. They both form subwords, and I'll take them in the same order. Okay, so Z forms, so these are two things. And the key observation is Z forms the trivial element. Why? This is what I emphasized earlier, right? So Z has a matching with nothing unmatched, because I just separated out the unmatched things into Y. So it represents a trivial element in the free group. Okay, that's what we showed when we said that this was a length. So now let's count these. So when I have a word X with a non-crossing matching, okay, so if it has R unmatched letters, so this is determined by, so you want to determine this word. If I know Z, I know Y, and I also know which indices are in Z and which indices are Y, then I know the letter X. I can rebuild it from these three pieces of data. So I know the word Y, I know the word Z, and which indices are unmatched. The remaining ones are in match. So if I know this triple, Y, Z, and there are indices, then I know X. Okay, so now some simple combinatorics. So what does this tell you? What is, I hope I have a pen. Yeah, let me make this guy black. So the choice of R indices out of N, of course, we learn in school is N choose R. Word Y we have no control over because these are unmatched, but it has length R, so there are 4 to the R. Okay, and what about Z? I'm just giving it a name. I'm calling it T2M. This is a word of length 2M, which is a trivial element in the free group. And so what we are left with is to count T2M. Okay, so that is the key point. And the warning here is N choose R is quite big. I mean, it's exponential in N. So it's the evil combinatorial term. We need to control T2M well enough to defeat this evil combinatorial term. Okay, so let me give a quick heuristic. What happens here? Okay, so this is a picture. So we can think of trivial words in the free group in terms of random walks. This is what's called a Cayley graph of the free group. Namely, if I start at the origin, the edges coming out of this correspond to A, B, A inverse, and B inverse. So a trivial word could be something like A, B, A inverse, A, B inverse, maybe A inverse, A inverse. Okay, so a trivial word in the free group, the one that I wrote just now was A, B, A bar, and then A, and then there was a B bar, and then an A bar, and an A. And then you'll see these two cancel with each other. Let's draw a non-crossing matching if you wish. These cross cancel with each other. Just keep canceling and you get the original word. Okay. So a trivial word in the Cayley graph, this is pretty much a definition of a Cayley graph, is exactly a random walk. So this is fine. These are paths, and this is a random walk. And the random walk takes you away or towards the origin. And the key point, and this is a key idea in a lot of results on negative curvature, not just with groups. In fact, the first important result I know of this nature is one of Dennis Sullivan. Mike Anderson gave a different proof at the same time of the result that manifolds with negative sectional curvature, universal covers of such manifolds, have harmonic functions on them. And Sullivan's description was that a string of results he had were all based on one simple idea. Namely that suppose I'm here and I take a random step, then 3/4 of the time I'm moving away from origin and only 1/4 of the time I'm moving back towards the origin. So this is not a symmetric random walk. You're not just going left or right. You're much more likely to go away from the origin than come towards the origin. Okay, so this one is not recurrent. It's not even ergodic. It has a Poisson boundary. There's a lot of interesting thing here. But the simple point is that you tend to run away from the origin. So the chance of returning is small and exponentially small. Okay, this can be explicitly counted more or less, but there's a twist to the tale. So given a path, we can count the number of paths. This is what's called a Catalan number. And the probability is, remember, a path of length m has m steps to the away from the origin and m towards the origin. So it's more or less the probability of a step away from the origin is 3/4 and towards the origin is 1/4. If this was not just more or less true, if it was true, you could get an explicit formula. But the catch is that if you are at the origin, you are guaranteed to move away from the origin. So there the probability becomes 1. Okay. So this was a heuristic to tell you that because of your tendency to run away from the origin, the fraction of the paths that return to the origin is bounded. Okay. Now, so to turn this into a complete proof takes work, but this work was done long ago by Keston in the 1950s. Okay. So here is the result. So let tau k be the proportion. So the proportion of random walks that end up at the origin, which is to say represent the probability that a random word of length k represents the trivial element. By the way, if k is odd, this is 0. Doesn't matter. And Keston showed that tau k is less than or equal to square root of 3/2. Here's the result for all free groups, free group on 2 generators. So let me just highlight the things we want. This probability is less than or equal to root 3/2 to the k. Okay. And as a result, the number is of course root 3/2 to the k times the total number 4 to the k. Okay. There's a little bit of an outline. Keston doesn't state it like this. What he shows is the limb soup is root 3/2, but actually log of tau k is subadditive. So from that you can deduce this. I have a little bit of an explicit deduction here, but let me skip that. So where do we get? Okay, we get with a calculation. Just a couple more slides and then I'm done. So here is a calculation. Remember, so I've changed notation to the notation in our paper. So I'm letting W and delta be N and R. Delta is now the proportion. R is N times delta. Okay. So what is W and delta? Remember, it had an N choose R combinatorial term. 4 to the R, this was unmatched letters. And then this was TK. Okay. So in terms of what we called this earlier, sorry, T2M. This was the T2M. And 2M is just N minus R. Okay. So T2M was exactly this, which we can put. So now I'll pull out all the 4s here. And so we get this. And now we use a bound on N choose R. This is a Chernoff bound. You can use more elementary bounds. You would all have heard of Stirling's formula. So this is of that same nature. This is an elementary bound. N choose R is less than exponential times something in terms of delta, which is delta is, remember, R over N. Okay, it grows at the level of N times delta log delta. If you want to get a rough idea what this is true, use your Stirling's formula, which will tell you N factorial is about N to the N plus half e to the minus N. Feed that in and you will get something of this kind. Stirling's formula is an approximation, not a bound. And this is slightly better than what you get from, well, not better than that. So it's of that nature. Okay, so we don't have anything really beyond that. Okay, so now we are in good shape. What do we know? N choose R. So this quantity here will go. So what is the probability? So probability, we get rid of this term. So when we take probability, we are quotienting. We just have N choose R, which is this term, and root 3 by 2 to the N minus delta, which goes here. So we regroup this and we get a probability is bounded by exponential of this quantity here, which we just bounded, and log root 3 by 2. This is the Keston bound on the number of paths. Okay. So now with this calculation behind us, let's try to understand what do we want to know? We want to know whether this probability goes to 0. Well, it's an exponential. When does an exponential go to 0? When the exponent is negative. Okay, if it's positive, it goes to infinity. If it's negative, so it's negative when this happens, minus delta log delta. And for delta small enough, we can show this is true. In fact, we can have a explicit bound, which is lambda 2 is 0.03. Okay, so since it's been an hour, I'll skip the next slide, which is we can refine this bound a little bit by just, let me just say, I chose y, z arbitrarily. Instead, we make a canonical choice of z, which is, and then our choices drop from 4 to 3 for y, for most of y, which looks very nice, but the numerical bound is only a very slight improvement. So since it's just past 6, let me skip the details of this. Let's just conclude. So here are my final remarks. First, our proof works for all non-abelian free groups. There's nothing special about 2. RNA corresponds to 2, but the mathematics is fine for all free groups. And then this is an additional result. I won't go into details of this. In fact, you should better ask Manjunath if you want details of this. It's not just that the average is lambda 2, but standard probability techniques will tell you that most words, that is all but an exponentially many, the fraction of unmatched letters is actually very close to lambda 2. Which is not 0.03, that's a lower bound for lambda 2. That's a true value, which may be 20% or whatever else, 0.2 or something like that. That's what experiments suggest. But what you can deduce is that for most words, the minimum number of unmatched letters is actually close to some lambda 2. Okay, and the final 2 remarks are just because, given the context, I thought let me try to look at this slightly more generally. So I like this result, but it's special to free groups. Is there a more general question at least we can ask? Well, remember, we can think of the length as being the word length in generators and their conjugates. This is an infinite generating set. Now, as is easy to see and well known, if I took 2 finite generating sets for a group, the lengths in the 2 of them are comparable. They differ by constants. But of course, lengths in infinite generating sets are not comparable to lengths in finitely generating sets because the generators have length 1. But if you took these nice infinite generating sets, which is conjugates of your finite generating set, then the ratio of length here is generically bounded. Okay, this is true for free groups. So let me just end with a question. For what groups does this hold? Okay. By the way, this is a loosely formulated question. Don't take it from me that this is some kind of expert view that this is important or anything like that. But I thought, let me try to end by saying, well, for all free groups, we have this result. These are techniques. Okay. But what would it be for all groups? There are other questions one can ask, but let me just end with this. And I'm ready to answer any of your questions.
Okay, Siddharth, thanks very much for this wonderful lecture. Now, as I can see, there are already lots of questions. So let me ask one by one. So the first question is, can you suggest some paper or books where I can find more ideas about this topic?
Well, I don't know about which part of this topic. This spanned, I think, several fields. So I assume you mean, so if you want to see this proof, Manjunath and I have a paper. And it's on the archive, but there needs a small correction had to be made. The small corrected version will go on Monday on the archive. It's already posted, but archive doesn't post on the weekend.
And
so after, yeah.
And
but if you want,
question,
more general background, maybe geometric group theory, there are many books about it. But this is, as I said, this is just this is a mix of many things. Yeah.
The second question is from these final remarks. What do you mean by most words?
What do I mean by most words? Okay,
Yes.
so I mean that you pick a random word, okay, and you have lambda 2. Okay, so then so I have a, so what do I know? I know that x, so I have the quantity lambda 2, let's say. Okay, so I'll take an epsilon. So I look at probability that let me take the length of xn by n, and I think you have a square root term. So suppose I take the probability that this is the fraction of unmatched words. Sorry, let me put my n a little better. I have this fraction of unmatched words minus lambda 2. That this is big compared to, I believe it's 1 over root n, or in fact epsilon over root n. For any epsilon, if I look at the probability of this, this is exponentially small, is less than exponent of something like that. Okay, so for most words, as you look at the fraction of words where the number of unmatched pairs differs from lambda 2 by a largish amount, okay, large compared to square root of n, and need not be large compared to n, then this, and in fact Manjanath conjectures into the 4 decay you have, then this proportion is small. Yeah.
Okay. So Gianluca, does it answer your question? I think it answers the question. Now there are more questions, so maybe it's a good idea if the speaker, if the concerned person can ask it himself or herself.
Yeah, I think now you
that would be nice. So I request the organizer perhaps to unmute the person who wants to ask. So raising
Dr.
hand is a
Gadgil,
good option.
my question is, could you mention that this is what everyone is unmuted now?
Yeah, I think too many people are unmuted.
I was asking, you said that
now we can ask.
Go ahead, please.
Please unmute yourself and ask the question.
Okay, I was saying that you said that this the length function is the maximal length function on the free group, which is conjugate invariant. So what would the maximality here be like? So what is the order in which it is maximal?
Yeah, that's a very good point. Okay, so there is a partial order, and this is an utterly naive partial order. Okay, so suppose we look at length functions. Yeah, so this is Gromov's green book, by the way, is a source for lots of these things. So some of the ideas go before that. So I'll simply say L1 is less than or equal to L2 if for all G in G, L1 of G is less than or equal to L2 of G. Okay, so this is a naive partial order. It's very easy to define this partial order. What may be less obvious is that there is a maximum because it's clearly only a partial order. What happens if every length is less at some point and greater at some other point, etc. Okay, so the general trick is that you look at the set of all length functions L, which map G to whatever it is, 0, infinity. Okay, so L is a length with all the properties, and you let length of alpha 1 is less than or equal to length of 1, etc. You have these conditions. So you look at the set of all these lengths, and for each point G, you define L max, let's say, of G as the supremum of L of G, where L is in this scribble, sorry, where L is in the script L. Okay, and this turns out to be maximum. So the maximum exists. This is bounded by triangle inequality and so on. Yeah, so maximum is with respect to this naive partial order, where it means point-wise maximum. This is only a partial order, but there is a maximum.
All right, thank you.
Okay, so here are actually two questions of the same nature that I would like to combine. So the question is, does this result hold for symmetric group of n letters and for the small cancellation groups?
Okay, so with symmetric group of n letters, it is a finite group. So if you're talking about things being comparable, nothing will, I mean, everything will hold for rather trivial reasons. Okay, so this result, yeah. So I'm taking this geometric group theory view that you take things as comparable. Okay, but as I learned from this really nice talk of Arpan, that people do work on effective bounds in finite group case. You may want to refine things and may be interesting. As far as the question is concerned, I just loosely formulated it while making this talk. I really have no idea whether it holds or not for, well, I mean, there are examples like abelian groups where you can work it out in 2 minutes, but for any non-trivial examples, I just loosely formulated it. Maybe people have worked on it. Maybe there is a literature which knows this, or there's no promise of anything that it's unknown or anything like that. But I don't know any case other than the free group. I mean, I've been working on the case for the free group, both as an interesting geometric combinatorial problem and its relation to RNA, but yeah, so I don't know. Yeah.
So
But
I have,
it's not obvious. Huh? Sorry.
Yeah.
yeah. Are there, do you see any mathematical constants down the road, and do any of them have an implication for biologists?
Yes. So does this have implication for biologists? Actually, this is
No. Wait. The first question is, do you see any mathematical constants down the road?
constant.
Mathematical constant.
What do you mean by mathematical constant?
So E and pi are very famous mathematical constant.
Do I see a mathematical constant down the road?
Yeah.
Well, I mean, all sorts of these limits give mathematical constants, like lambda 2 is a mathematical constant, but I don't think it's an important mathematical constant. Yeah. So, I mean, any quantitative result with an estimate will give you, I mean, there is a fraction, so it is a mathematical constant. It is interesting that it is positive. Actually, you have a point there, because you do have phase transitions in groups and so on. So where the phase transition occurs is often interesting, though there it is often at half or such things. So similarly, you have a number, but I don't see, I mean, I don't think something like lambda 2 is an especially important or interesting mathematical constant. Yeah. And the
And
second
any implication for biologists?
implication for biology of a particular mathematical result, no, this result, but this result, by the way, sorry, let me say, it has a meaning in RNA. Okay, so the meaning is the following, that if I take a random long strand of RNA, okay, the question is whether you need to have folds which go a long way from here to here. Okay, so I'm drawing these non-crossing matchings because I can't draw RNA folded. Do you have bonds which cause parts of RNA very far away to fold from each other, or all the foldings are only very local? So what this result tells you, because you converge to a positive constant and hence you have this concentration result, what this result tells you is that you can have only local foldings, and that gives you something that is near optimal. So there is a meaning, at least in terms of RNA behavior. Okay. On the other hand, if you want to apply it to biology, you have to really start with biological questions about RNA. Yeah. So when I started, I did consider certain things. For example, one important thing is allosteric structures, and these things illustrate them nicely. So allosteric structures are structures where you have, so this is a concept for proteins. I mean, it works for RNA as well, where a protein has two different local minima, which are very different from each other. So remember, a protein, as I said, it starts as a line and then it folds. So it can fold in one way and it can fold in another way. And these two are very different folding from each other. Okay, so these are called allosteric structures. This, for example, is very important in real life. So what's called mad cow disease, bovine spongiform encephalopathy, and various of these prion diseases as they're called are because our proteins in the brain, they switch from one configuration to the other. And what causes it is if that you have, there's an autocatalysis. Once you have a few proteins that are what are called misfolded, folded in the wrong configuration, it causes slowly the other things to misfold. And this disease progresses over 30 years and so on. That's why it has remained, it never got selected out because it's a very slow acting disease. They were called slow viruses, but they're not viruses. So there are allosteric structures, autocatalysis. Yes, so there are phenomenon, and as I said, you want to try to understand the origin of life. You want to understand what properties of RNA facilitate them. So no particular mathematical result will straight away give it to you. What is true here, and that's why I worked on it, but over a decade ago at some length, then I moved to other things. I moved to other things for a certain reason, which I'll come to in a moment. What is nice is that there is actually an attractive mathematical model which is reasonable for biology. So there may be lessons for it. So if you're an experimentalist, you understand this and you want to think about free groups and you want to conduct an experiment, you can look at RNA and ask how random is it from this point of view. So you take actual ribozymes in nature and see whether they are somehow atypical in a way that you can capture in their words in the free groups. It is possible. You have to make a connection with experiments. I don't know the answer. In general, the larger lesson is, of course, two larger lessons. One of which is that you should, of course, understand biological questions and understand the biology well. The other larger lesson, though, which is why I moved away, is that especially true with protein foldings. You see, biomolecules are a product of evolution. So they're like engineered things. So you don't take a car and study it mathematically. I mean, or even this computer on which I'm lecturing. If you try to have a mathematical theory, when designing it, you can put in the mathematics. But if it's already built, you don't try to reverse engineer with a mathematical theory because a lot of things are optimized to work in nature. And they're also local optima. So because of the role of evolution in biology, one must be quite careful about using this kind of toy mathematical models. That is not to say that they're not useful. It is just that they should be used with due care and due humility. Okay, so yeah.
Yeah, and thanks for this. And since you mentioned phase transitions,
Yes.
Could you state the algorithmic complexity of finding out the Watson-Crick length of a given string?
Yeah, so that is actually is a very good question. So I do find it in my in the polymath project, and when I plotted these things and so on, I did compute it. For example, this was an explicit computation using a simple recursive method. But this recursive method grows exponentially. Okay, and as far as I can tell, and this is Manjunath's view also, I don't think there is a simple way. Okay, so there is the usual problem. We don't really know how to prove things are hard. If P is NP, everything could be polynomial. So so on the one hand, okay, there are a few interesting things one can say. You see, so let us first formulate the correct algorithmic question. So the correct algorithmic question is to ask if the length is bounded above by a certain number. If you can find the upper bound, then you find the best one. Okay. So you want to know whether the length is bounded above by a certain number, which is asking whether there is a non-crossing matching, which leaves only, let me be concrete now. Let's give some concrete numbers. I have a string of 100 letters. I want to know if there's a non-crossing matching so that 90 are matched, only 10 are unmatched. You see, this is NP because the way I can prove there is such a matching is simply exhibit it for you. I can give you this picture and you can just check letters are matched with their inverses, count those that are not matched. Okay, so this is NP in the sense that you can give if an answer, once you have the answer to an upper bound, you can prove the upper bound. Okay, I don't know if it's NP complete. Perhaps it is not. Perhaps it is even. Perhaps it is in reality, but it is just very hard to prove because this is a bit of a rigid problem. So yes, so the algorithms that I just use, I mean, so in real life, sometimes things are not so hard, even if theoretically they're supposed to be hard. That is, you can do useful things, and I have done useful things just calculating many of these things. They have not just here, they have resulted in a different theorem and so on. So sometimes things work in practice, even if theoretically they're large, but then they'll blow up for large n. So in practice, when I was trying to find the proportion, it does start blowing up when you have 40 and so on length things. The naive algorithms are exponential. It is NP. So NP implies exponential anyway, at most exponential. I don't know if it's NP complete. The problem, again, let me just say it briefly. So the problem is if you try to think about how are you going to find a matching, okay, then let me just, yes, this is an interesting question. I'll answer it here. So how are you going to find a matching? The problem is fundamentally, if I see a here and let me be algebraic, I see an alpha and an alpha bar here. Should I match these or not? Now I can match them, but if I try to be greedy and match whenever I see an alpha and alpha bar, I may do something quite terrible. That is to say, maybe I have a bunch of betas here and a bunch of beta bars here, and the numbers are the same. Okay. So I chose this, but this is a horrible way of matching it. If instead let me just color this. Sorry, if I instead matched betas to the beta bars, then almost nothing will be unmatched. Only the alpha and alpha bar will be unmatched. So what I'm saying is that if you choose one bad choice, it could lead to a very bad suboptimal everywhere. So this is the reason why this is complicated. So yeah, it's like Sudoku. If you think you put a wrong number, things can go bad, even if it solves your local problem. So fundamentally, computationally, things are hard of this nature. If your things are locally solve your problem, but it globally messes things up, which happens here. Yeah.
Okay,
Sir,
so
if I may ask a question.
I
Thanks
request.
for that elaborate answer and the insights.
Thanks. Yeah, are there further questions?
Yeah, so Indrajit Devnath, he has raised his hand for a long time.
Okay,
so maybe
sure.
the organizers can unmute and he can ask a question.
Yeah, he can unmute. Indrajit, are you here?
Okay, I mean, you can also write on the chat box if you want.
Sir, good evening, sir. If I may ask a question. Just, hello.
Yes, I can hear you.
Yeah. Good evening, sir. The talk was very, very good, actually.
Thanks.
So I'm Krishna from Pondicherry University. I have a rather general question. So
okay.
I would like to take up research in TDA, topological data analysis. So I would like to know what should one get started or equipped with, like in the basic terms, to get into TDA.
Yeah. No, I am not an expert in topological data analysis. I'm familiar with it to some extent. You should know algebraic topology. That is one thing. Okay. And the second thing that I think I can just quote, I said the same thing in a different context, but let me quote Professor Rajiv Karandikar from 2 days ago. I think you all heard him say this, that if you want to apply mathematics to any domain, you must learn that domain. Okay. So if data is just an amorphous quantity to you, I mean, it's just a bunch of numbers and you have to play around with it and use some topology there, then it won't work. Okay. I mean, it'll work not work very well. Okay. So you have to be immersed. So one thing is, as far as topology is concerned, the topology in topological data analysis is algebraic topology, not very complicated ones. It's an understanding of homology and things like Morse theory, which let you compute homology. You need a good understanding. By the way, this is a general meta point. That is, when you're applying one field in another field, whether it's within or outside mathematics, typically the important thing is not knowing a huge amount, but knowing the core of it extremely well. So you need to understand algebraic topology, not necessarily a huge amount. You don't need a Steenrod square or any characteristic classes, but what you need to know it well. And the other thing is that you should be familiar with data analysis. You should be used to using SciPy and NumPy or whatever else in whatever language you like, and plotting things, working with your hands with numbers. But beyond that, I'm not an expert. You can, I'm only weakly familiar with topological data analysis.
Okay.
Beyond
And
that,
one,
I can answer.
yeah. Okay, and okay, and one more question, sir. So how is the trend of TDA in India? If you can answer, if you can just give some details on, because research in
Trend of
TDA,
what?
as far as trend of, I mean, how is TDA practiced in India? So research and all this.
Yeah, I don't actually know people working in topological data analysis. I'm sure, I don't know of too many actually. I know one person who did a bit, but he's gone off to Germany. So I haven't yet met somebody who does TDA in India.
Okay.
This
Okay.
doesn't mean there aren't people doing TDA in India. The person I know closest to that is Vijay Natarajan here in computer science, who does do topology applied to data analysis. But this is a little bit different. It's not what one calls TDA. It is interesting work. Certainly there are, it's quite likely that just I haven't come across them. So I can't really tell you much about this. Yeah, if you're saying.
Sir, I can add to this.
Yeah.
Priyavrata is currently working on topological data analysis.
Yeah. Who is Krishnendu? I didn't hear the name.
Priyavrata.
Okay, I don't know. Yeah.
Thank you.
So there is another question in the chat.
Yeah, so anybody wants to ask any question? Yeah, in the chat there is a question that could you please specify what maximality of length functions would mean? What would be the order of the length function?
Huh?
What would be the order?
I think this was a question asked already earlier, right? Here I wrote this function. L1 is less than or equal to L2 if it's pointwise less than or equal to L2. So you say one length. So length means at each group element you give a number. So there is an obvious partial order on functions on any set where you have pointwise ordering. That is, at each point one is bigger than the other. Okay. The non-trivial point is that in many of these situations you do have a maximum. Otherwise, if you, namely, you can look at all length functions in this class and take the maximum of this pointwise, and this becomes a length function. It satisfies triangle inequality and so on. It is very interesting that it happens. It's been used. It's the Kobayashi metric from long ago is of this nature. As I said, yeah. I learned of this, and a good way of learning all these things is from Gromov's classic metric structures on Riemannian and non-Riemannian spaces, with the caveat that nobody pretty much actually understands that book, but you still can learn quite a lot from it. Yeah, I mean, there are people like Mike Anderson who do, but yes, but most people don't actually understand that book, including me, but you can learn a lot from it anyway. Yeah.
Yeah. Okay, so
could I ask one more question?
Yeah.
Yeah, instead of, this is a very typical question actually, instead of taking the linear string, what happens if we take a cyclic one?
Oh, this is conjugacy invariant, right? So actually in this case, it makes no difference. So what you're saying is if it's only cyclically ordered, in this particular case, in general, it could lead to subtleties, but in this case, as it turns out, if you think of it on a circle, what you're doing is just pushing things out from the end. So conjugacy invariant means that so if you took a cyclic string, you get exactly the same thing as the linear string. Yeah.
Right.
Okay.
Right. I see.
So any more question? Okay, so if there is no more question,
what if we have an array of such strings? Sorry, not I mean a rectangular array.
You mean you have several elements in the free group? Yes.
Yeah, so it's like you have a matrix basically.
Right.
You have an n by n matrix, and then you want to match alpha and alpha inverse and beta inverse. But you could match it row wise or column wise, whichever
you can
way
make
you want.
variations of these. This depends on the non-crossing condition. You have to correctly specify what you mean by non-crossing, right? So for the linear case, it's clear what you mean by non-crossing. So you could generalize this by looking at an appropriate configuration, and this non-crossing definition which is sitting in front of us, you could try to have a variation of the non-crossing definition depending on your context and study this question. There are variations of these. Yeah, so this particular thing, you see, I mean, okay, I don't know much and I don't do much combinatorics. The thing is that there are three views of this. This is a combinatorial view, but it's also biology and it's also algebraic. And I primarily tend to look at it as an algebraic question. If you turn it into a rectangular array, you still retain the combinatorial question, provided you have your correct notion of non-crossing. Okay. Many of these techniques
The notion of non-crossing can be extended directly. It just applies in the column or in the row.
Okay. Yeah, you can. I mean, it can be extended directly, but not uniquely. You can decide how to extend the non-crossing, right? Yeah. So yes, there are ways in which you can generalize this to the square. I don't know what happens. Perhaps you can use the similar ideas. Perhaps not. I don't know.
Okay. Okay. So.
Okay. Thanks a lot.
Yeah. Sure.
So if there is no more question, then on behalf of the organizers and everyone, thank you, Siddharth, for this wonderful session. I think people really asked lots of questions, and that shows that it was very interesting to everyone. So I thank you virtually, and I request everyone to thank virtually on Zoom. So I give it over back to the organizers. So Somo, could you please?
Thanks a lot. Thanks a lot. Thanks for this opportunity. It was a lot of fun, and I hope people enjoyed it too. Thanks.
Thanks a lot, Professor Gadgil, for this wonderful lecture and answering so many questions. And also to Dr. Krishnendu Gangopadhyay for chairing this session. Thanks a lot. Thanks to all.
Thank you.